Okay, section 5.3, conservation of energy. So this is where things start to get really interesting because we're going to bring together our work concept, our potential energy concept, and our kinetic energy concept, and they're all going to come together into one type of problem. And that's where it starts to make a lot more sense for me. So I think you'll see once it's in action, it makes a lot more sense when we put them all together into one problem. So we'll be talking about closed systems. I am going to show you a few pictures from your textbook. So if you get a chance, you should go and look at these. These are different types of energy. I'm not going to go through them all. You can read them. It's just kind of it's good to be familiar with them because we're only really introducing potential, kinetic, and work at this moment in time. But there's a lot of other types of energy. And you can see radiant, electrical, gravitational, thermal, sound, nuclear, elastic, chemical. So there's lots of different options here. But this is on your textbook, and I'll leave that for you to read. So we're going to talk about energy transformations. That's part of what conservation of energy is. So again, if you want to pause it and read this, I'll just give you the quick highlights. So we have something called photosynthesis, which is a process that it's an energy transformation. Okay, so it takes radiant energy from the sun, it turns it into chemical energy stored in food molecules. Okay, in that process, things also warm up a bit, which we call thermal energy. Animals, including humans, we eat the plants, we transform that chemical energy into chemical energy in our muscles, and then we can turn that chemical energy into either kinetic energy, thermal energy, so we could do work and things in our environment. It's how we move. Okay, so it's this transformation of energies. But what we'll see is that energy is in a closed system is fixed. And this is one of the biggest concepts you'll encounter in physics. It's huge. It's in science, okay? And so the way we currently view science and the world around us, the law of conservation of energy, it's not a theory, it's a law right now, which is big. Okay, so it says the total amount of energy in the universe is conserved. Okay, think about that for a minute. So the total amount of energy in the universe is fixed. There's some number. It's gigantic, but there's some number. There's a certain total amount of energy in the universe, and this total never changes. So new energy cannot be created out of nothing, and existing energy cannot disappear. Now that's a really big one because if something has energy, it has to go somewhere. Okay, so the energy that exists can only be changed from one form into another. So when an energy transformation occurs, no energy is lost. It's just changing its appearance. It's changing the way it exists. If you stick with this physics stuff into grade 12, we'll start talking about how matter and energy switch between the two. Okay, and that starts to get really big and heavy on the brain. For now, though, we're going to stick with our classical Newtonian physics and mostly mechanical physics, so stuff we can see a little easier and are a little bit more comfortable. So you've got two red boxes here. The first one is something I'll call an ideal system. That's a perfect system. So there are no losses, no friction. Everything is just ideal. Okay, it makes it easy to solve. The numbers work out generally nicely. We don't have to worry about lost energy. The second one is a non-ideal situation. That's where there could be losses. Losses to friction, losses to thermal. There's energy moving, not necessarily out of the system, but out of the part of the problem where I want it to be. Okay, and we'll do an example near the end where hopefully that becomes clear. Okay, so we have a diver on a board, a 10-meter high diving board, and I'm not going to go through all of this. I'm mostly just going to erase to show you. Again, this is in your textbook so you can follow along. So at the very top of the diving board, the diver is 10 meters off the ground. They have a lot of potential energy, but they have no kinetic energy. So this is zero, and their potential energy would be their mass times gravity times their height above the reference line. In this case, the reference line is the pool, okay, way down here. So if we look at the numbers, we see we have an EG of 6.4 kilojoules. Their EK is 0 because they're not moving, which gives me a total mechanical energy of 6.4 kilojoules. So if you remember, mechanical energy is the combination of gravitational potential energy and kinetic energy together. Okay, now this number right here is really important. Because this is a closed system and it's an ideal system, that total mechanical energy can't change. That means it's going to be 6.4 in every single aspect of this question. Okay, so as we slide down here and we move to the next part. So now the diver is 5 meters off the ground. So we could again do another EG calculation, or we could go 65 times 9.8, only this time we would use 5. Okay, so we would have half that potential energy we started the problem with. So now we're down to 3.2. We can jot that down here. Okay, but as I said in the initial part, the mechanical energy is still 6.4. That can't change. So that means all of the energy that we started with in gravitational potential energy, which was 6.4, it's now decreased to 3.2. That means that energy had to go somewhere, and the somewhere is into kinetic. Okay, so I don't even need to make a calculation on that. I know those two have to balance and add together to make that 6.4 again. Okay, so now at the very bottom of the problem, okay, so we're at the very bottom. Now I have a potential energy of 0 because the d, or the height of the diver relative to our reference line, is 0. So I have 0 joules in potential energy, which means of the 6,400 joules or 6.4 kilojoules that I had for mechanical, that means now everything has gone into kinetic. Okay, so the transformation in an ideal system, all of the potential energy from the very top got turned into kinetic energy at the very bottom. Okay, and now we can use that. We want to find, oh, we didn't ask for it, okay, but if we wanted to use this right here, if I know the kinetic energy at the very bottom and I know the mass of the diver, I can actually use that to find their velocity. Okay, because I know this is 6,400. I know this is 1/2. I believe the diver was 65 kilograms. And we could solve for v squared. And you might be saying, hey, you know what? I could do all of that with kinematics. And you would be absolutely right. Okay, you could do it all with kinematics. And then let's square root it. So 14 meters per second would be our velocity. But there are trade-offs. Kinematics, you have to keep track of vectors and directions. You may have to break things up into two-part problems. With energy, it's all a scalar, so direction isn't as important, which we'll see in future questions can be really, really helpful. Okay, so here's the sample problem. We have a 1.1 kilogram camera, slips out of a photographer's hands while he's taking a photograph. Ouch, that hurts. The camera falls 1.4 meters to the ground below. So what is the camera's gravitational potential energy relative to the ground? So they've given us the reference point, which is important. So my gravitational potential energy, just going to fill in all those little pieces. Again, the math side is not particularly complicated. It's just multiplication. What we'll have to keep track of is the thinking part. So I think we have about 15 joules, okay, of potential energy. So using the law of conservation of energy, determine the camera's kinetic energy at the instant it hits the ground. So if we have a camera here with an EG of 15 joules, oops, and an EK of 0, by the time it falls to the ground, EG has turned to 0, and all of that potential energy has to become kinetic energy. Okay, so use the camera's kinetic energy to determine the speed at the instant it hits the ground. So if we say EK 1/2 mv squared, as we just did in the last problem, I put the 15 in for the joules, half, the mass is 1.1, and I have to solve for v squared. Try and do that relatively quickly. 15 times 2 divided by 1.1 and square rooted. It should be about 5.2 meters per second is the velocity when it hits the ground. And if you want to do a little test, by all means, try it with your kinematic equations. See what happens. You should get 5.2 meters per second. Okay, so practice one. You might want to pause this and try it. Okay, so I'll let you pause it and I will come back and take it up. Okay, so we have a 0.2 kilogram ball thrown straight up from the edge of a 30-meter tall building. Okay, now this should ring bells from our 2D motion. So here's a ball, here's 30 meters. When we did this with kinematics, it was a two-part problem. We had to figure out all the way up to the top, break the problem up, then go all the way from the top down to the ground. Okay, what you'll see with energy is we can actually be a little bit more efficient and be a little faster in solving. So I have a mass of 0.2 kilograms. I'm 30 meters off the ground to start, and I have an initial velocity of 22 meters per second. You'll notice it doesn't tell me any angles either, which is kind of handy. There's that vector piece that's not required for energy. So the ball moves up to a maximum height and then falls to the ground at the base of the building. Use the law of conservation to solve, assuming the reference level is the ground. Okay, so that's an important piece. So our ground is our zero. What is the total energy of the ball at the start? So our total energy is our mechanical energy. That's our Eg plus our Ek. So this is mass, gravity, distance or height, plus 1/2 mass, velocity squared. And if we punch those in, 0.2, 9.8, 30 plus, there's no way I'm going to fit all of this in here in this little space, so I may have to scroll or erase. And then, oops, I almost forgot the squared. And then my initial velocity is 22 squared. Okay, so if we do a quick calculation in all of this, 0.2 times 9.8 times 30 plus 0.5 times 0.2 times 22 squared, we get 107 joules. And I'm going to guess the book probably rounded that off to 110. Yeah, of course. Okay, so we have the same answer as the book, which is nice. What is the velocity of the ball at the maximum height? Okay, so I'm going to just erase this for a second so I have a little bit more room to write. So the velocity of the ball at the maximum height. Well, we know that from our 2D motion that v equals 0. Okay, well if v equals 0, that means Ek equals 0. So if we want to find the maximum height, we have a total mechanical energy, that's Eg plus Ek. I already know my total mechanical energy from part A is 110, we'll say. My Eg is mgd, and this is 0. So now if you look, I have the mass, I have gravity, and now all I have to do is solve for d. That's a pretty slick way of coming up with the maximum height. And it should be, oops, that's a wrong number, 110 divided by 0.2 divided by 9.8 should be 56 meters. Okay, so if we look, they got 55 meters, pretty close. Okay, so 56 meters. Now you have to remember that's also measured from the reference line. Okay, so that is right here. That's 56 meters. So no two-part problem required, which is kind of nice. What is the velocity of the ball when it hits the ground? So again, we know that the total mechanical energy is 110. It says nothing about air resistance or any external factors, so this is a closed system, an ideal system. So at the very bottom, all of my energy that I started with is going to be converted to kinetic. So my 110 that I started with for mechanical, I have 0 potential, and I have 1/2 mv squared. Okay, so if we solve that really quickly, 1/2 ball was 0.2, and I'm going to have to solve that squared term. So let's go 110 times 2 divided by 0.2, and then square root. I should get 33.2 meters per second is my velocity. And again, I don't have to write direction because it's a scalar and I'm just interested in magnitude. Okay, so this is a non-ideal example. So I've changed up and I've introduced that lost piece in here. So if we have a 65 kilogram bike and rider, they're at rest at the top of the hill. She begins her ascent down a 200-meter long hill inclined at 35 degrees. So a couple of pieces we're going to have to extract. This in here is 35 degrees. This is 200 meters. Okay, so, and you have to be really careful here. The 200 meters for this question is not the height. Okay, so if we look here, this is a sine question, so you have to do a little bit of work. Sine 35 equals the height over 200. So this object from the ground or the reference line is sine 35 times 200. Make sure you're in degrees. Let's say it's 115 meters in elevation change. That's a really big piece to know. Okay, so if we looked at this expression now, and I'm going to use this top one. What is the kinetic and gravitational energy of the biker at the top of the hill? So let's go with blue for a minute. EK1 plus EG1 gives me the total mechanical energy at the start of the problem. So EK is 0 because it's not moving. It said it's at rest. And then I would have mass, gravity, and distance or height. Okay, and I'm just going to save myself a line. The mass of the biker is 65 times gravity 9.8 times the elevation change is 115. So we have 73,255 joules as our mechanical energy to start the problem. That's also this side of the equation. Okay, so there will be times when we'll use that whole big equation. I'm just a little bit limited on space. If the bike mountain, that's the interaction of the bike and the mountain slope, uses up 20,000 joules of energy, and it's going to use it up in friction, so thermal energy, the ground warms up, the tires warm up, dirt is kicked all around. What is the velocity of the bike rider at the bottom of the hill? Okay, so there we go. Our EK, come on, EK1 plus EG1 equals E lost plus EG2 plus EK2. Okay, and again, this is the thinking part. None of these calculations are super difficult. They're just multiplications. So we know this left-hand side has 73,255 joules. That's how much energy was started in the problem. Okay, the energy lost we're given right here is 20,000. The EG, that's the potential energy at the bottom of the hill, is 0. Okay, and then lastly, we have our EK2, which is 1/2 mv squared. Okay, so if we take our 73,255 minus that 20,000, okay, times it by 2, divide it by 65, and then square root it, whew, I get a velocity of 40 meters per second. That dude is moving. Okay, so double check that. It's late at night. Maybe my numbers are off. I'm a little bit shy on time. What is the average force of friction working on the bike during that ride? Well, it traveled 200 meters. This is where the 200 meter comes in. This is the amount of energy, that 20,000 joules. That's how much energy is lost to friction. So we can think of that as work equals force times displacement. So if we put our 20,000 in for the energy that's lost, we have a force we don't know, and we have a distance of 200 meters. By the time I solve 20,000 divided by 200, I get a 100 Newton force of friction acting on the bike the entire time. Okay, now last thing, and I'm going to wrap up. I know this is getting a little bit long. If I had more time in class, I would show you this. These are just different energy representations. So the circle here, this is one way of showing interactions of systems, cars, and roads for this example. This is another nice table you can see, and it's just a visual perspective. It has the exact same conservation of energy expression at the top, only it uses little bar charts to show you where energy is going. So let's try this really quickly. So we have a 1,500 kilogram car traveling at 10 meters per second. It runs out of gas while approaching a valley. Okay, so the driver immediately puts the car in neutral so it will roll. Now, if we assume this was an ideal situation and the car wasn't moving, then this would just roll back up to the height it started at. That would be a perfect system. Okay, but now this car is moving. Okay, so we'll still assume there's no friction or no losses in here, but the car is moving, which means it has kinetic energy as well as potential energy. So that kinetic energy should allow the car to go higher. And what we need to do is figure out how high. Okay, so for case 1, we'll do no friction, no losses. So EK1 plus EG1, so we can figure out those numbers. We have the velocity and we have the height over our reference line. So we can start with 1/2 mass times velocity. So there's our EK1 plus our EG1, which is our potential. I have 1,500 mass times 9.8 times 10. So this is the left side of the equation. Okay, I'm just going to call it left because I'm not going to be able to fit everything in here. So 0.5 times 1,500 times 10 squared plus, this is going to be a big number, 1,500 times 9.8 times 10, 220,000 joules. That is the left side of the equation. Okay, so now if we're looking at this problem though, and we want to know how far up the hill does the car roll. Okay, so at this location right here, we still need to have 220,000 joules. Okay, so if it rolls to a stop right here, we also know that EK is 0. So on the right hand side of the equation, because we're doing no friction, no losses, this guy is not a part of this problem. EK is going to go to 0. So this boils down to being 220,000 joules on the left side is equal to EG2. Okay, let's see if I've left myself enough room. Probably not. So the mass of the car, I'm just going to write over this for now. My apologies. mgd, and then we'll solve 220,000. I need an answer 0 there. Mass is 1,500 times 10 times d. Okay, and I know this is getting a bit long. I'll try and go a little quicker, but I wanted to make sure I showed something that had all the parts to it. 220,000 divided by 1,500 divided by, I put 10, I guess I should have put 9.8 to be more precise. I'll start that again. 220,000 divided by 1,500 divided by 9.8, 14.96. So let's say that's 15 meters. So if we're looking at this question, did the car get to the gas station? Absolutely, it made it to the gas station so it can refill. Okay, now the next part of the question, what if we actually take into account friction? Okay, so I'm just going to get rid of this piece. Okay, the mechanical energy we started the problem with is no different. It's still going to be 220,000. So if the car coasts to a height of 5 meters up the second hill, determine how much thermal energy has been created in the car road earth system. Okay, so if we start with EK1, EG1 equals E lost plus EK2 plus EG2. Now before you madly dash in, we already know this side. We don't know the lost, which is what we're trying to figure out. Because the car comes to a stop, this is 0. And we know the last term is the mass times gravity, and it said it only got 5 meters up the hill. Okay, so we have our 220,000 E lost and then we just have to multiply this together. 73,500. Let's extend that page a little bit. So now 220,000 minus 73,500, 1,400, oh, sorry, 146,000, oh my goodness, it's late at night, is how much energy was lost to friction. Okay, so that's the heating of the tires, heating of the road, all of those things happen in joules. My bad. Okay, and because so much energy is lost to both the road, the tires, and that type of thing, then the car doesn't actually roll up anywhere near as high as it could have. So remember, without friction and not even moving, it would roll 10 meters high. Okay, but we introduce the friction, we get an awful lot of losses, and the car doesn't go anywhere near as high. Okay, that was a very long one. I appreciate your patience and time. Hopefully it set you up for solving these 3 questions, 1, 2, and 3. Thank you again.